Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for the introduction. Okay, good morning everyone. So I changed my title of the talk a little bit to incorporate more work that I've done with GPU. So it's about application of GPU for high performance network processing. Sorry. Okay, so here's the outline of my presentation. So first, I'll start with motivation. I'll briefly introduce what's the challenge in building high-performance networking equipments and why GPU is attractive for it. And after that, I'll introduce GPU. I'll show how GPU works and what are the advantages and challenges for using GPU for network processing. And I have done two projects by utilizing GPU for network processing. So first is SSLShader, and the second is PacketShader. So I'll spend most of time talking about SSLShader and briefly explain PacketShader, which is a previous work of SSLShader. And then I'll finish the talk with conclusion and future work. So what's the motivation? So unlike old days, today's networking does a lot more complex functions than simply forwarding packets. So for example, many companies use VPN gateway to connect companies' network in multiple locations through the internet, and intrusion detection systems are introduced to protect servers and users from hackers. And there are also many other network equipment that requires complex processing like application-aware switching or video transcoding, to name a few. And I'm sure some of you want to put more complex functions into the network, right? So the challenge with network doing more complex functions is sustaining the performance while doing it. So if you add functionalities in a network device, you may need another hardware accelerator for it, or the performance will drop. So the graph that I'm showing you is performance of software router for three different applications. So first is simple packet forwarding, and second is routing, and third is IPsec. So navy bar here represents the throughput for 64 byte packets, and green bar is for the real network trace from research network called Evelyn. So a single server can achieve almost 10 gigabits per second for simple packet forwarding, while it drops down to 1.4 gigabits per second as it runs IPsec. So this is 7 times performance drop. So as this example demonstrates, adding new functionalities in network equipment can substantially drop the performance. So how do we deal with it today? So there are several existing solutions to help complex network processing. So whether it's based on custom hardware or commodity hardware, network equipment typically use acceleration cards. So here I differentiated existing solutions into 3 categories. So first is ASIC. ASIC is basically custom built chip that does complex processing. And second is FPGA, which is programmable hardware at the gate level. And FPGA has advantages in that it's programmable, but it's not really simple as programming in C. And
so in your previous slide, the 7 times drop in performance, that was what, for pure software?
Yes, pure software router.
I see. So above all of these, there's just pure software, CPU.
Yes.
And that's what goes 7 times slower.
Yes.
And that's unacceptable, so people are doing these other things.
Yes.
I see, okay.
So, and third category is network processors. And so network processors are typically composed with general purpose cores and specialized block for cipher or routing table lookup. So these are programmable in C, but it's not as easy as programming general purpose CPU. So because we need to deal with special blocks and like many cores in network processors. So what's the problem with existing solution? So I want to note that like network processing is not only complex, but also there's growing demand for flexibility. So for example, when new cryptographic algorithm can be desirable for like more secure and faster processing, and in data center networks, there's a lot of need for custom protocols to optimize the performance in it. So if you look at existing solutions, ASIC is not programmable at all, and FPGA is quite difficult to program. And network processors are programmable, but if specialized block doesn't match your needs, then performance will be not as good as you expect. And finally, all these solutions are quite expensive. For example, 10 gigabit net FPGA card is about $3,000, and high-end crypto card is over $10,000. So what can you do about it? So we can use GPU for network processing. It is fully programmable and very cheap. You can buy high-end GPU for only $500, and it provides high computation capacity. So now let me explain why GPU is attractive for network processing. So GPUs are originally developed for graphics processing. So the key characteristics of GPU is in massive parallel processing. So here I'm showing the abstract view of CPU and GPU. In CPU, most of transistors are devoted to cache and control unit, and only a small portion is for ALU, where the actual computation is performed. So CPU is highly optimized for single-threaded processing with like pipelining, superscalar, or out-of-order execution. And GPUs, on the other hand, dedicate most of its cores for ALU to achieve high raw computation power. So GPUs have hundreds of cores and process lots of data in parallel. So now let's think about how to make good use of those hundreds of cores. So it's very challenging to achieve like high performance out of GPU if we program the same as for CPU. So GPU uses different programming model called the single instruction multiple threads. So with this model, GPU executes the same code for multiple data in parallel. So I'll explain with example code that as n-dimensional vectors. So this is the typical CPU code that has length and vector. And on the right side is GPU code for doing the same work. So they differ in that the CPU code iterates over the data to add multiple data, while the GPU code simply add individual elements that each thread is corresponded to, and it runs n threads at once to add all the elements in parallel. So
thread ID x.x.
So that's that's the constant provided by CUDA compiler language. So if you use that variable, then when you launch the thread, it will be automatically translate to the thread number.
Okay. It's always called x, is it?
So there's y and g. So
you get 3.
Yeah, there's 3. It's 3-dimensional. So you can use y and g as well.
But if you want 4, you're game over.
I think so.
Okay.
So it supports up to 3-dimensional, I think.
Okay.
I never tried above that. So I frankly don't know about it. So now I showed you that GPU exploits like massive parallel processing to achieve high throughput, but why is it attractive for network processing? So I'll explain advantages of GPU in terms of computation power and memory access latency and memory bandwidth by comparing Intel CPU and NVIDIA GTX 580. So network processing such as hashing, encryption, or network coding or compression requires a lot of computation. The good thing is that GPU has an order of magnitude higher computation capacity in terms of instructions per second. So, and hence, the GPU can help like compute-intensive networking processing. And network processing includes lots of cache misses. So, for example, routing to table lookup has random memory access pattern and brings lots of cache misses in CPU. And GPU typically runs hundreds of thousands of threads simultaneously. And with massive number of threads, GPU effectively hides cache misses by switching to another thread when there is cache miss. And network processing also can benefit from high memory bandwidth of GPU. So, for example, in software router, we forward packets and it's actually coming from the network interface to host memory, and then it's processed and then sent out to the network interface again. So it involves data copy at least 4 times. And as a result, the further network processing has only small portion of remaining memory bandwidth for bandwidth. So GPU have a lot more memory bandwidth than CPU, and it can help memory bandwidth hungry applications as well. So GPU has several advantages over CPU for network processing. So however, exploiting GPU for network processing is challenging for a number of reasons. So GPU rely on massive parallel processing to achieve high performance. So we need to find parallelism in network processing. So for this, we use extensive batch processing and parallelize each cryptographic or routing table or like other algorithms when possible. And secondly, network applications are very sensitive to latency. So we do lots of optimization to reduce latency in GPU processing. And also parallelization of our algorithm is important to reduce the latency. And third, network workload varies over time. So for packet processing, we may process thousands of packets at once to gather parallelism, but waiting for those thousands of packets can increase delay indefinitely. So on the other hand, if we offload like single packet processing to GPU, it can be actually much slower than processing in CPU. So to solve this problem, we use opportunistic offloading. In other words, we balance the loads between CPU and GPU depending on the load level. And now, I'll move on to SSLShader to show you how we overcome those challenges. So SSLShader is about how to accelerate SSL processing by utilizing GPU in a cost-effective way. So let me start with the motivation behind SSL acceleration. So I'm showing you here a screen capture of NDSS 2011 paper submission site. And NDSS is a security conference. And if you look at the URL, it uses plain text HTTP. So obviously there's a gap between security research and practice. So when you log into this site to submit a paper, your password and account name are sent in plain text. So anything sent in plain text over the internet is a target of eavesdropping. So who does eavesdropping and where? Here I list 3 cases. So public Wi-Fi without encryption is an easy target for hackers to capture other people's traffic. Some governments are known or suspected to inspect traffic. There is censorship in the name of national security. And a media box can modify payloads of packets in flight. So a company called Naviweb once conducted targeted advertisement using this technique. So they inserted cookies of their websites into the HTTP requests that are going through some ISP, and they collect user information by this way without user's permission. So sending information in plain text is not safe, then how can you avoid it? So we already have a solution. We can use SSL. So SSL stands for Secure Sockets Layer. So it is underlying technology behind the HTTPS or SMTPS or etc. It provides server authentication, data confidentiality, and content integrity. So let me show how it works. So suppose a client is trying to communicate with a server. First, it initiates a plain TCP session. The client and the server exchange the secret key using public key algorithm. So the public key algorithm protects the key even when someone is eavesdropping on the communication. And with the exchanged key, the client and the server start actual data transfer using symmetric cipher and hashing. So SSL has been out there for past 15 years, but still most websites do not employ SSL. Less than 0.5% of websites registered for SSL certificates. And so why don't we use SSL for every website? So for small sites, they don't recognize the necessity. I showed you earlier that even security researchers don't pay attention. And for large sites, the cost of using SSL can be quite huge. So because SSL requires lots of computation, the computation cost of SSL is the problem we are looking at in this talk. So to get a sense on computation cost of SSL, we ran a simple benchmark with the web server. And this benchmark is run with the only single CPU. to eliminate the multi-core scalability issue. So for this benchmark, we used we make the client to generate HTTPS and HTTP requests indefinitely, and compare, and by varying the content size, we'll get the load. And for connection setup, we see about 20 times more computation for HTTPS, and for data transfer, we see about 50 times more computation code for HTTPS. So what should we do now?
Well, that wouldn't matter, of course, that wouldn't matter if only 1% or 0.1% of the time was taken in communication anyway. The server had real work to do. See what I mean?
So
yeah. If it's down in the noise anyway, then 50 times noise, who cares?
So that's, yeah, I see the point.
You're focusing exactly on this.
So it's focusing on static contents, right? So if we are doing like backend, considering backend web servers doing a lot of complicated stuff, then that's correct. So, but still, like a lot of YouTube contents are static, right? So there's a lot of portion of web traffic that is static content, so there's no backend server performing anything. So still, SSL computation is quite a challenging problem. And if you look at the practice, if you look at login to Facebook, they protect the login page only, and they don't protect other page at all. So I believe that's because computation cost of SSL. So what can you do about it? We can buy more servers, or we can buy hardware SSL accelerators. But both solutions are not cheap, they're expensive. And our suggestion is to use GPU and offload SSL computation to it in a cost-effective way. So to demonstrate that our idea makes sense, we have designed and built SSLShader. It offloads SSL computation to GPU and delivers high performance. We use commodity hardware, and so the SSLShader is cost-effective, and it's implemented as a reverse proxy. So existing servers can take advantage of it without modification. So now I'll move on to how we implement cryptographic algorithms on GPU. So we implemented Cipher Suite with RSA, AES, and HMAC SHA-1. We choose this Cipher Suite because it is one of the most popular one. And RSA is used for key exchange at the SSL connection setup, and AES and SHA-1 is used for actual data transfer to encrypt the data and prevent tampering. And our optimization of GPU are in twofold. First is exploiting parallelism with parallelization of algorithm and batch processing. And second is reducing data copy overhead, which is costly in GPU processing. So I showed you earlier that parallelism is essential to fully exploit GPU's capacity. So where can you find such parallelism in SSL processing? So at the coarse grain level, each independent SSL sessions can be processed in parallel. And second is each SSL session is composed with a small unit called SSL record, and depending on the cryptographic algorithm, these records can be processed in parallel as well. And finally, each SSL record can be divided into smaller pieces depending on the cryptographic algorithm. So of course we exploit all three levels of parallelism in this work. First, I'll show how we parallelize cryptographic processing with an example of RSA. So let's look at how RSA works. For both decryption and encryption, it uses modular exponentiation. The difference between encryption and decryption is that in encryption, the exponent is typically very small prime number like 3 or 17. In decryption, exponent is 1K bits or 2K bits integer, which is really large. So thus, calculating this modular exponentiation in the decryption takes a lot more computation than encryption, and typically the server, for SSL processing, the server performs the decryption, and it is the bottleneck at the server side. So, and exponentiation is basically lots of multiplications, and these multiplications are on large integers like 1K or 2K bits as well. So for faster calculation of RSA, we parallelize these multiplications. So how large integer multiplication works? Suppose you are multiplying two 1K bit integers in a 64-bit system. A 1K bit integer is basically 16 64-bit integers, And naive way is to multiply each word in one integer to each word in other integer and add all the results. So this way requires 256 multiplication. And if you have s words in a large integer, it requires s square multiplications. So parallelizing a large integer multiplication using many processing cores is not trivial. So from now on, I'll use more human-friendly example. Suppose we multiply two 3-digit numbers. You can think of each digit as a word in a computer. So in this case, we are multiplying two large integer, which is composed with the 3 words or 3 digits. And we multiply each digit in the first number to each digit in the second number, and the results are 9 numbers with 2 digits and trailing zeros. And all multiplications are independent and can be parallelized. However, the parallelizing of accumulation of these 9 numbers are not trivial. So there are dependencies due to the overlapping digits and propagation of carries. So how do we deal with it? First idea is to separate the processing of Loword and Hiword to remove dependency. So here Loword is blue digit and Hiword is red digits. So by separating Loword and Hiword, we can process 3 numbers in parallel among 9 numbers. We also process carries separately to remove dependency. So let me show how it works.
I didn't get what's the difference between low and high? Just when you multiply 2.
Yeah, 2 digits. It can be up to 2 digits, right?
Okay.
Yeah, and Loword, there's Loword and Hiword.
For each individual multiplication.
Yes.
There's 2 words. Okay. And then what's this table?
So this table is Loword and Hiword for multiplicating each like 3 digits, the other 3 digits in second number. So there are 9 numbers for Loword and 9 numbers for Hiword.
So you've written the 2 operands. Okay.
Yeah. So first we have to separate storage for intermediate results and carries, and we start with accumulating Loword results to the intermediate results. And if you add, there will be carries. And if there's any carry, then we store in a separate carry storage. So it takes 3 steps to process 9 Lowords in parallel when we have 3 processors. And we process the Hiword the same way. And next is accumulating these carries to the intermediate results. So this step is basically same as accumulating the Lowords and Hiword results. So this process takes typically 1 or 2 steps, and in the worst case, it can take s-1 steps. So our algorithm has an order of s time complexity when you have s processors. So you might think that if you use s-square processor to multiply all the multiplication parallel and add it later, but that actually reduce the utilization of a given number of cores, because there will be dependencies in adding it, and some cores will remain idle during the adding phase. So it utilizes all cores fully the whole time for the processing. So from initial implementation using this parallel multiplication, we optimized RSA a lot more. And we applied several common optimization techniques like Chinese remainder theorem and Montgomery multiplication and so on. And we parallelized these known algorithms when possible, and there are like GPU-specific optimizations. And after all optimization, we observe about factor of 20 improvement over the initial implementation. But I'm not going to explain all those details in this talk, so please read our paper for details. So now I'll show performance of our RSA on GPU.
Just before you go on that previous slide, some of these people have been studying multiplication for a long time.
Yes.
Right. So how much of this is stuff that you developed, or was GPU specific or somehow, and how much was just take the standard ideas, apply it to GPUs, job done?
So common optimization techniques, those are like existing ones for sure. And parallelization of those are our ideas. So we parallelized it when possible, but it's really hard to find literature that parallelize these algorithms. And GPU-specific optimization, we studied like NVIDIA manual over and over to optimize the GPU algorithms. So, So, but some of previous work on RSA also does some of this work, but the big difference is that they used parallel multiplication, which has time complexity of order of S log S, and ours have order of S for when we have same S processors. And ours perform about 8 times faster than their work in terms of latency and throughput. So
that's a good result.
Yeah. So now I'll show performance of our RSA on GPU. So red bar here is performance of GTX 580, and blue bar is for a single CPU core. And we show for 1K certificate and 2K certificate separately. So if you look at GTX 580, it performs 73,000 operations per second for 1K bits and 12,000 operations per second for 2K bits. And recent Intel CPU performs about 3,400 for 1K and 2K bits. So GTX 580 performs like faster than 20 CPU cores, 20 to 30 CPU cores. And table below is the latency for each cases above. So GTX 580 achieves its maximum throughput under 7 milliseconds for 1K bits and 21 milliseconds for 2K bits. And these numbers are low enough to be used in SSL processing. And the previous work was over like several seconds when they achieved maximum throughput, and for minimum they achieved it around like few hundred milliseconds, which is not really practical. So it's the main contribution in our work.
So since that's got 512 messages, at some point are you going to talk about the opportunistic offloading when you shift from CPU, which is
okay. Yeah, that's a good question. So these results are from batching 512 messages for 1K bit case and 256 messages for 2K bit case. So I'll show you what happens without batching in the next slide. So earlier I showed you that there are 3 different levels of parallelism in SSL. And so far I explained about parallelization of each algorithm with an example of RSA. And I show about batching now. Sorry about that. So to give a sense on how important batching is, here I'm showing the GPU performance without batch. So it means that GPU is processing only single operation at each execution. And y-axis is relative performance to a single CPU core running at 2.6 gigahertz. And what we observe here is that performance is pretty worse than a CPU core. It is because there are enough parallelism in the cryptographic algorithm.
So why is it 1 core, not 6 cores, 12 threads?
So that CPU, like various CPU, have different number of cores, so we compare it to single core only in this case. So like we have done experiments with 4-core system and 6-core system and sometimes 12-core system, and it depends on, it's really hard to compare with the single CPU in terms of like performance because there are like varying number of cores in CPUs. So yeah.
So here, low is bad for GPU.
Yes.
Okay.
So it's pretty bad without batching, right? Only AES decryption is performing very better than single CPU core. So this is performance of batching, and the batching size depends on the algorithm. So for AES decryption, we use 32 messages in a batch, and for RSA we use 512 messages, and other algorithms are 4,000 messages at each execution. And we see about 6 performance improvement over a single CPU core. And you see significant difference between RSA and other algorithms. So the difference between RSA and other algorithms is in the ratio of computation to copy. So in other algorithms, they copy a lot of data, while RSA copies small data and does a lot of computation. So to process data in GPU, we take 3 steps typically. So first is copying data from CPU's host memory to GPU memory, and then we process it and then copy back the results. And to quantify the data copy portion, we ran a benchmark without the data copy. So in this case, we assume that data are already placed in the GPU, and we measure only kernel execution time. So you see that it performs 2 to 4 times faster compared to data copy. So it means that it spends more time on data copying than actual computation. So to minimize copy overhead, we take advantage of GPU's copy hiding capability. So this is synchronous execution case. So each step runs sequentially after one step another. And if each step takes time t, then it would take 3t for one execution. And modern GPU supports pipelining of copy and execution. So in this case, 3 different steps can overlap with another when there's no dependency. So if you launch multiple tasks, that different steps of different tasks can overlap with another to hide the copy overhead. So this is the performance we see with this pipelining. So we observe 36 to 51% improvement in maximum throughput, and GPU achieves performance of 9 CPU cores for AES and 14 CPU cores for SHA-1. So as a summary of GPU cryptography, we show that GPU can perform as fast as 9 to 28 CPU cores depending on the algorithm. So, and our RSA implementation on GTX 580 shows 92,000 operations per second, which is the fastest one using GPU. And GTX 580 performs about 12 gigabits per second of AES and 47 gigabits per second of SHA-1. The performance of $500 graphics card is actually superior than high-end hardware SSL accelerators. And there are lessons we run through using GPU. So first is batch processing is essential to fully utilize a GPU. And second, AES and SHA-1 are bottlenecked by data copy overhead. So this bottleneck will be mitigated in very near future with I/O performance improvement using PCI Express 3.0 or integration of GPU and CPU.
So can I ask, why do you copy from CPU memory to GPU memory? I mean, how did the data end up in CPU memory in the first place? Because the network card put it there, right? Mm-hmm. So the network card just put it in GPU memory in the first place? So technically that's possible, but you're going to need support of adding new chip into the motherboards. So basically, how DMA works is, I'm not really an expert on those areas, but you cannot copy from NIC to GPU directly without support of other chip that does DMA. So there's, you can do it if you have a separate DMA chip for it. Okay, so there's a kind of opportunity there. Because after all, if you're spending you can bottleneck on it.
Yeah, that's true.
And lastly, these figures are assuming perfect batching. Is that
yes?
Which, as you pointed out earlier, is in tension with latency.
So that's actually a nice question. So these numbers are we batched only to the point where we get reasonable latency under 100 milliseconds. So in all these results are in latency of under 100 milliseconds. And if you are willing to compromise latency further, then you can see a little bit higher throughput, but not much. For all of those.
I see. So what you're saying is that the batching in practice does not disturb latency too much?
Yes.
According to your measurements?
Yes, if you optimize each algorithm sufficiently.
Data is smaller, but it has more smaller copying operations between GPU.
So copying is also done with batching. So before copying, we move all the data into one aggregate location and then copy it at once. So if you actually copy much smaller data, the overhead is actually much larger. So I'm not sure, but you have to copy at least few megabytes to get optimal performance. And less than that, you will see less throughput. So based on GPU cryptography, we built a SSL proxy that leverages it. And we designed SSLShader with 3 design goals in mind. So first is easy integration with existing applications. And this is the reason that we built it as a reverse proxy. And second is effectively leveraging the GPU. So to do so, we batch cryptographic operations and balance loads between CPU and GPU. And third, we design SSLShader with multi-core and NUMA systems in mind to reflect the hardware trends. So again, batching is essential to exploit GPU's full capacity. The problem is that you cannot wait for a fixed batch size in networking applications. So we use dynamic batch size for GPU processing, and to do this, we put cryptographic operations in the queue before we need to we process it, and GPU pops all cryptographic operations in an input queue at once and process it in parallel. So basically, batch size will be automatically tuned at the speed of cryptographic operations coming and GPU's processing speed. So still, there's a problem. If there's not enough batch in an input queue, then it can slow down the processing. So for optimal performance at the light road, we use opportunistic offloading. And to do this, we make a separate queue for GPU. And if the length of input queue exceeds certain threshold, then we move all the data into GPU's queue. So GPU processes only data in the GPU queue. And if the input queue length stays below certain threshold, then CPU processes it. So this way, the GPU will process data only when there's performance benefit of doing so. And to scale I'm sorry, I forgot one thing here. So, and the threshold is set to the point where GPU starts performing faster than a single CPU core. So this way, GPU will never perform worse than CPU. So to scale performance with multi-core systems, we spawn multiple threads that match the number of cores. It's called worker threads, and each worker thread performs network stack handling and cryptographic operations as well. And these many worker threads shares a single GPU through a single GPU queue. And so many worker threads move data into a GPU queue, and GPU process it together to gain more parallelism by gathering cryptographic operation coming from the multiple cores. And if data is processed in a CPU, a core processes its own data only. So the rationale here is that moving data from one core to another will incur more cache misses, and more cache misses and performance will degrade. So we also consider NUMA systems.
Do you do anything to forbid packets going out of order?
No. So we do not consider ordering here. So basically, if there's two data, and if one goes through CPU and the other goes through GPU, then there can be reordering happen in this case. But it's not really big problem in our benchmark. But yeah. Sorry, can you? So considering that each processing takes like 100 milliseconds, then like you will be served like 100 milliseconds later, and that's not really a big problem, I think. So one thing we do is that we control the amount of data put in the GPU queue at once. So even if reordering happens, the difference between like the processing time will be less than like a second.
So did you try to see the performance of things like TCP and stuff? If you were to measure the performance of classic TCP connections,
I have a latency distribution at the end of my evaluation. So it has cumulative distribution of latency for like thousands of clients. I'll show that later. Okay. So we also consider NUMA systems in the design. So the picture I'm showing is high-level view of a system with two NUMA nodes. It has two CPUs, which have separate memory, and each NUMA node has a separate I/O controller to connect NICs and GPUs to CPU. The problem is that if data moves across NUMA nodes, it is much slower than accessing data within the NUMA nodes. And to minimize data crossing across NUMA nodes, we use separate process for each NUMA node, and there's no communication between two processes. So GPU is only shared within a NUMA node in a process that has multiple worker threads and possibly multiple GPU threads. And for eval,
Can I ask a question about the previous slide? How random is the duration of the whole encoding operation? So is it like very predictable? It will take, I don't know how much time, so the separation will be easy, or you actually have to guess how long it will take?
I'm not following the question. Can you clarify?
Split your data stream into two nodes, right?
Yes.
So do you have to worry about if some processing will take longer and some shorter amount of time to kind of try to balance, or you know exactly how much processing each part will take?
So
Just half.
okay. So balancing between so in this in our experiment we balance loads by using separate network interface, and each network interface forwarding traffic only to single NUMA node. So in that case, if traffic is coming through only one network interface, there will be problem. Other half will be just doing nothing. But another way would be you can have like separate load balancer or those kind of things in the front end, or we can configure each NIC to distribute to all cores, but that will make the data crossing across NUMA node, because a NIC is bounded to one NUMA node as well. Right? So I'll move on to evaluation now. So for evaluation, we benchmark the web server with SSL, and we compare SSLShader using GPU acceleration against Latency with OpenSSL, which uses CPU only. And we run SSLShader and the Latency together in a single server for this experiment. So SSLShader is reverse proxy, and we run this proxy in the machine that Latency is running. So backend server is running in the same server. And the server is equipped with 2 hexa-core CPUs, so total 12 cores, and 2 NVIDIA GTX 580, and 2 dual-port 10 GB Ethernet NICs, so it can support up to 40 gigabits per second of traffic. And we look at 3 different metrics. So first is connection handling performance. For this test, we use very small content, static contents, and it stresses CPU and GPU with the RSA operations. And next, we look at the response time distribution by varying the load. So the purpose of this test is to look at how opportunistic offloading works. And finally, we look at the data transfer rate at various content sizes. So first is HTTPS connection handling performance. We use small static contents for these experiments, as I mentioned earlier. The client repeatedly requests and connects, requests the contents, and disconnects. So we run experiments with both 1K and 2KB certificates, because 1K bit certificate is most popular one today. However, it is not believed to be safe, and 2K bit is recommended. So we ran a test for 2K bit as well. So SSLShader improves performance by 2.5 times for the 1K bit case, and 6 times for 2K bit case. And we find that this 2.5 times increase is quite similar for GPU's RSA performance. We see 29,000 connections per second, while a single GPU can perform 92,000 operations per second. So we profiled a CPU usage in 1K bit case and find that Linux kernel is taking more than 60% of CPU cycles, and it's the bottleneck in this evaluation. So now let's move on to the latency. So we look at the latency at the light load. So here 1K connections per second in this experiment, and x-axis is the latency in log scale, and y-axis is a CDF. And blue lines are result of Latency, and red lines are result of SSLShader. So we observed that latency of SSLShader differs less than a millisecond for lower 90% of cases. And SSLShader shows even lower latency for higher 10% of cases. So it clearly demonstrates that opportunistic offloading algorithm intentionally use CPU instead of GPU under light load. So we also look at the latency under high load. So for this, we increase the rate limit to almost maximum throughput achieved. So as you can see, SSLShader achieves much higher throughput. So we achieve 29 connections per second in this case with the SSLShader and 11,000 connections per second for Lighty, and latency is even lower. So
can you go to the previous slide?
Okay.
At light load, why is SSLShader 90th percentile? Why is the 90th percentile for SSLShader better?
It's not better for lower. You mean above like 90 percentile or lower 90 percentile? Above. So I think it's problem with the Lighty scheduling connection issue. So in SSLShader, we try to schedule every connection equally. So when there's cryptographic operation to perform, we mark the timestamp on each cryptographic operation. We perform like in order, all cryptographic operation in order. But I don't know how Lighty works, but they somehow performing bad for some connections. Maybe starvation problem, but I'm not sure. And finally, we look at the data transfer performance by varying the content sizes. So here I'm showing the relative data performance of SSLShader against the Lighty. So we observe about 2.1 times higher throughput for smaller contents. And as the content size grows, the proxying overhead becomes larger than benefit of GPU offloading, and SSLShader performs slightly worse than Lighty. And typical web content size is pretty small, like under 100 kilobytes, and we believe performance benefit as small contents outweighs the smaller performance loss at larger content sizes. And the peak throughput SSLShader achieves is 13 gigabits per second for at the 4 megabyte content size, and it stays constant after that. The peak throughput of Lighty is 16 gigabits per second at 64 megabytes, and it stays constant after that. And I'd like to note that it's not really an apples-to-apples comparison, and SSLShader involves like additional data copy from the backend web server to the kernel and kernel to the SSLShader. So because it has to do the proxying, so it's not really an apples-to-apples comparison.
Couldn't you just replace? I mean, SSL is fairly standard, right? I imagine it's a library for most of these things. If you replace the library rather than use the proxy, would that just go away that quickly?
So I haven't done that yet. So integrating it into a application requires a lot of effort actually to directly integrate it. So there was a ongoing work on making OpenSSL using GPU, but their performance is pretty bad because it is really hard to do extensive batching when you use OpenSSL framework. Because so Lighty uses event-driven. So Lighty is using like built as an event-driven application. So there are only few threads. So if you want to batch like 500 messages, that they should not block at the SSL processing, but the current mechanism blocks when you do the cryptographic operations. So that's the problem when you're dealing with OpenSSL. So as summary, we show that GPUs are good for cryptographic operations, and we implemented RSA, AES, and SHA-1 algorithms. And with our implementation, a $500 graphics card can perform even faster than high-end hardware accelerators. And on top of the GPU cryptography, we built a SSLShader, which is a SSL reverse proxy, and it transparently accelerates SSL for existing servers, and it leverages GPU efficiently. It achieves up to 6 times faster connection handling performance and 13 gigabits per second of maximum throughput out of single box. So the current bottleneck we observed is in the Linux kernel scalability and copy overhead, and we're trying to mitigate these bottlenecks now. So far I explained about how we use GPU for SSL processing, and now I'll move on to PacketShader. The PacketShader is previous work of SSLShader. So it differs SSLShader in that it process data at the packet level rather than session level as SSL does. So the motivation behind PacketShader is software routers are based on commodity hardware and it's driven by software. So it is flexible, cheap, and has easy development environment. It is popularly used for research, but for developing new protocols or running experiments. However, it is rarely used in real network because of its low performance. So by low performance, we mean two things. First is the performance drops significantly for small packets. And second, performance drops as processing becomes more complex. So we came up with how GPU can do work, how GPU can help in this case. And so based on that idea, we made a PacketShader. So PacketShader is a high-performance software router exploiting GPU. It achieves 40 GHz per second of IP version 4 and version 6 routing in a single server for 64-byte packets. And PacketShader is divided into 3 different parts. And first part is packet IO engine, and second part is GPU acceleration framework, and third is application that runs on top of packet IO engine and this framework. And since the framework and GPU acceleration shares lots of ideas with SSLShader, I'll mainly talk about how we optimize the packet IO engine this time. So what's the problem with the current IO? To find out the cause, we look at how CPUs are used when we receive 64-byte packets through the network in Linux. And the table here shows the CPU used categorized by functions. And first, we observe that lots of CPU cycles are spent on memory subsystem to allocate buffer for each packet received. And second, we see lots of cache misses as packets received from network is not in the cache. And device driver code takes lots of CPU cycles for handling interrupts as well. So we use 4 techniques to remove this CPU bottleneck, and I'll show some of the details. So first optimization is huge packet buffer. So in Linux, when you receive packet, it allocates a buffer for each packet payload and metadata separately. So this overhead increases when packet size gets smaller, because to fill the same bandwidth, you have to have more packets with the smaller packets. And instead of allocating buffer for each packet, we allocate one huge buffer for a chunk of packets. So we also use very small metadata instead of a full SKB. So in Linux, SKB holds over 200 bytes for various networking protocols, but we do not need this for software router. So we keep the metadata compact as possible, and this way we amortize the memory management overhead by allocating memory for a bunch of packets at once. And second is batch processing as in SSLShader. So in PacketShader, we exploit batch processing at many levels. So at the fine-grained level, the NIC aggregates multiple packets into one PCIe transactions when packets are small. And secondly, a device driver receives a chunk of packets from a NIC to host memory at once. And when device driver passes them to the user level application, it passes a chunk of packets per system call. So we apply batching for various levels in the processing, and we also use software prefetching. So it is done when driver passes a package to the user application. So we need software prefetching here because packets are scattered in memory by 4 kilobytes units when you receive it from the NIC, even if regardless of their sizes. So when you gather it to pass it to the user application, we do software prefetching to minimize the cache misses.
So to do this, you are modifying the network stack code itself?
So it's not really modifying. We built up our own networking stack instead of using Linux networking stack. So we modified device driver, and we made our own API to access packets through the driver.
So you built a whole new stack?
Yes, but it doesn't have much stack. I mean, it just has the stack to pass packets from NIC to the user level application, and it doesn't have TCP or IP or anything else.
Okay, so that might be a big win overhead-wise if you say, let's throw away the generality of the stack and just build a custom one.
Yes.
So you might get a huge factor of improvement. Just
But
from that.
like, if you have Linux and if you just want to do like forwarding packets or recording packets, you have to have overhead of doing a lot of like other data structures, right? But if you have this kind of stack, you can do other things at user level efficiently just by building your own. So that's our work. So you can build whatever you want to do on top of this packet IO engine. And what we built is we built IPv4 router and IP version 6 router and IPsec and OpenFlow switch on top of it using GPU.
So by specializing the network stack for a limited range of
Yes.
software routing applications, you don't, I mean, just that, never mind GPU, just that might get you a big win.
Yeah.
Has anybody else done that? It seems like an obvious enough idea.
So most of previous work focus on like optimizing like I/O interface between NIC and the driver and user application, but I don't remember any work that completely get rid of existing stack and building new like optimized I/O engine. I don't recall any work. So Click modular router actually uses the device driver that is provided. They modify somewhat to use batching. Yeah.
Right, but they get rid of a lot of existing.
Yes.
You avoid all the existing networking code.
But still they rely on like SKB and other Linux stuff. Yep.
Same general.
It's the same general. Okay.
Yeah.
Thanks.
So how effective batching is. So here I'm showing you the throughput by varying the batch sizes. The result using a single core is around 1 to 2 gigabits per second for receiving and transmitting and forwarding. But as batch size increases, the throughput increases accordingly, and a single core can achieve 10 gigabits per second for a 64-byte packet. So we can receive 20 gigabits per second and transmit 16 gigabits per second and forward 10 gigabits per second with the single core. And the reason that transmission is slower than receiving is because we did not spend much time optimizing transmission. We spent a lot of time optimizing reception.
So no GPUs here.
No GPU.
Okay.
It's just receiving packets and transmitting packets. Okay. So there's no processing error. We just dump packets when you do it, when you receive packets. So it's packet IO engine performance using 8 cores, the total system with the 4 dual port NICs, so it can support up to 80 gigabits per second. And what we see here is that we achieve 80 gigabits per second of transmission regardless of packet sizes, and 60 gigabits per second of reception, and 40 gigabits per second of forwarding performance. So this is quite amazing result, given like previous work achieves around less than 10 gigabits per second for a 64-byte packet. And
How would you compare it to proper packets in a full packet? Instead of experimental small packets, if you were to use the same.
you mean using real network trace? You mean using real network trace? Or?
Yes, or the others still handled by packets.
So it has various packet sizes, so 64 bytes. And the bottleneck here is not in the CPU for all cases. So it's on the IO hub that Intel platform uses. So we use the dual IO hub platform, and it has problem in the receiving side. So that's the reason that receiving performs poorly than transmission. And the maximum capacity of this IO hub is 40 gigabits per second for forwarding. So that's the bottleneck here. And this bottleneck is also shared when we use GPU. So GPU has to communicate over the IO hub as well. So on top of this packet IO engine, we developed 3 GPU applications: IP version 4, version 6, routing table lookup, and IPsec those. And IP routing table lookup is bottlenecked by cache misses in GPU. The routing table lookup has random memory access pattern, and typical routing table size is over 200,000 prefixes, and it's hard to fit them in cache. And third application, IPsec tunneling is popularly used for VPN. So it relies on two cryptographic operations. First is encryption, and second is hashing. So we use AES counter mode and HMAC SHA-1 for our implementation. So for AES counter mode, we parallelize it at 16 bytes block level, so we take advantage of fine-grained parallelism in the algorithm itself, as well as in the packet level parallelism. But SHA-1 is not parallelized due to the dependency. And we evaluate these three applications by comparing GPU acceleration against the CPU-only version of PacketShader. So both of them takes advantage of packet I/O engine that we have optimized. And for experiments, we use two servers connected back-to-back. So PacketGenerator generates 80 gigabits per second of traffic, and PacketShader receives it and processes it and forwards it back to PacketGenerator. And each server is equipped with two quad-core CPU and two GPU and 4 NICs with dual 10 gigabit Ethernet ports. So it can process up to 80 gigabits per second, theoretically. So here's the results. We ran experiments with minimum packet size and maximum packet size to represent the worst and best scenarios. And the red bar represents the GPU accelerated version, and blue bar represents the CPU only version. So we see that about 3.5 times performance improvement for IPsec and 4.7 times for IP version 6 router for 64 byte packets, and 1.3 times for IP version 4 router. And the maximum throughput we achieve is 40 gigabits per second, that is bottlenecked by I/O hub. And for IPsec, we achieve 20 gigabits per second of maximum throughput. And it is also bottlenecked by I/O hub because unlike IPv4, we have to copy all the payload into the GPU for IPsec, so the throughput is cut into half in this case. So as summary of PacketShader, our evaluation shows that we can perform very fast packet forwarding by utilizing GPU. And our contributions in this work is ours is the fastest software router out of single box, as far as I know. And we have built, and our work shifts the bottleneck from CPU to I/O. So for now, we don't have bottleneck of computation. And we achieved all this at the user level processing. So that also distinguishes our work from the other works. The key factor of exploiting parallelism is exploiting parallelism for GPU processing and extensive batch processing at all stages of processing. Okay, so now I'll conclude this talk. So I showed that GPU is an effective solution for network processing with two examples, PacketShader and SSLShader. And our contribution in this work is in twofold. So first, we implemented various algorithms on GPU and showed that GPU achieves significantly higher performance over CPU. And second, we implemented several useful techniques to effectively utilize GPU, batch processing, pipelining, and opportunistic offloading of those. And these techniques are generic enough to be applicable in other GPU applications as well. So I have 3 future works in mind regarding the PacketShader and SSLShader. And the first one is extending PacketShader to support multifunctional processing. So the current version runs one application at a time. So, however, in a real router, the packets may go through different processing. So we are thinking about click-like framework for this. But the challenge is that when we have a batch of packet and packets in a batch have to go through a different path, it's quite hard to process it effectively. So we are currently working on this project. And second is we want to generalize the GPU processing framework that we built in SSLShader so that we can apply it to other GPU applications or many core systems. So like batching, opportunistic offloading, pipelining are essential to exploit GPU under varying loads or like when we have to process small data in parallel. And we are trying to generalize those ideas to incorporate other projects. And last one is building, a scalable network stack in many core and NUMA systems. So we observed that SSLShader is bottlenecked by data copy and TCP IP stack in the Linux kernel. And it's not taking advantage of packet IO engine we built for PacketShader. So we are trying to build upper layer networking stack like text TCP IP and other stacks on top of packet IO engine that uses batch processing so that other network application can take advantage of it. So that's it for